The moon is still hiding secrets from us, and that's extremely disturbing. There's a side of the moon that no human has ever seen with the naked eye in all of history. None. No matter where you were born, what century you lived in, or how powerful your telescope was. Since the first human eye opened on this planet, the moon has always spun in perfect sync with Earth, showing exactly the same face all the time without a single exception. For 40,000 years of human civilization, half of an object that controls our tides, stabilizes our axis, and was essential for complex life to emerge here was completely out of visual reach. This isn't some minor astronomical detail. It's one of the most disturbing puzzles in planetary science. And the more technology we develop to probe what's there, the bigger the problem gets. To grasp why this matters, you need to understand what that invisibility cost us over time. The mechanism hiding the far side is called tidal locking, or synchronous rotation. Over hundreds of millions of years, Earth's gravity created tidal forces on the moon that gradually slowed its spin until the time it takes to rotate on its axis matches the time it takes to orbit Earth. Result: it always shows the same hemisphere to us. Always. This isn't an elegant cosmic coincidence. It's inevitable physics. And it created a unique situation in the solar system. We have a massive, nearby satellite we've studied for millennia, and half of it was completely inaccessible to direct observation. For millennia, astronomers built models of what the moon was like based on half the available data. The Greeks calculated its size and distance with surprising precision. The Babylonians predicted eclipses years in advance. The Maya built extraordinarily accurate lunar calendars. But every one of them, without exception, was working with half the object. It was like trying to understand a person by only looking at the left side of their face. You think you get it. You trust your models. Then, when you finally see the right side, you realize it wasn't anything like you imagined. That happened. And what was revealed shattered decades of assumptions all at once. What happens when you lock a moon? To understand the scale of the problem, step back and see what tidal locking really did to the moon physically. When the Earth-Moon system formed about 4.5 billion years ago, the moon spun much faster. It had its own days and nights. The side we never see today was regularly lit by the sun, like any point on any other celestial body. But Earth, being much larger, exerted asymmetric tidal forces on the moon. Forces that tugged slightly on the moon's gravitational belly toward Earth, creating torque that slowed its rotation, millimeter by millimeter, over geological eras. That process likely took 100 to 200 million years to complete. Too slow for human observation, but fast enough on cosmic scales that it finished long before complex life existed on Earth. The issue is what that process did to both sides of the moon over time. As rotation locked in, the moon's internal heat distribution shifted. The Earth-facing side endured continuous tidal forces, which may have influenced where magma rose and volcanism was most active. The result is the most dramatic asymmetry we know on any solar system body. The near side is covered in vast dark plains called lunar maria, huge basalt lava floods that filled impact basins billions of years ago. The far side has almost none of these. Its crust is thicker, nearly double in spots. The terrain is rougher, older, more primordial. The two hemispheres of the same object seem to have endured completely separate geological histories. And tidal locking is the original mechanism that split them, while keeping one from our view. There's even a hypothesis linking this asymmetry directly to the moon's origin. But to get there, we first need to cover what happened when we saw the far side for the first time. 1959, the shock. In October 1959, the Soviet probe Luna 3 pulled off an orbital maneuver that took it around the moon and beamed back to Earth the first images of the far side in history. The photos were grainy, blurry, primitive by today's standards. But they were enough to deliver a genuine shock to the scientific community. What showed up didn't match any reasonable prediction based on the near side. No vast dark maria. No smooth lava plains. A surface far more pocked with craters, far more rugged, far more ancient-looking. The Soviets hastily named the features they could make out, and some of those names are still used today. But the far side's most stunning feature wouldn't be properly mapped for decades, until high-res orbital missions. It's the South Pole-Aitken Basin, a 2,500-kilometer-wide, 8-kilometer-deep impact scar on the far side South Pole. For scale, The entire continental US could fit inside it with room to spare. It's one of the largest and oldest impact craters known in the solar system, likely formed over 4 billion years ago by a catastrophic object. And it stayed completely unknown to direct human observation until the space age. A structure that size, hidden by tidal locking, waiting 4.5 billion years to be found. That sums up the problem. The moon as a dead archive. This is where one of the most fascinating and under-discussed aspects of the lunar question begins. Earth is geologically hyperactive. We have plate tectonics, a process that constantly destroys, recycles, and remakes the crust, subduction old rock into the mantle and creating new rock at ocean ridges. It's great for life, but catastrophic for the geological record. The oldest rock ever found on Earth is about 4 billion years old, and it's an extreme rarity, preserved by geological fluke in spots that escaped recycling. The story of Earth's first 500 million years is basically erased. The moon has no plate tectonics. It's an archive, a geological deep freeze preserving solar system formation material with fidelity Earth can't match. Apollo mission rocks are 4.5 billion years old, literally some of the oldest solid matter samples we have. But the Farside may hold something even more valuable. During the late heavy bombardment about 3.9 billion years ago, the inner solar system endured a phase of unimaginable violent impacts. Asteroids and comets hammered the rocky planets, hitting Earth, Mars, Mercury, and the Moon in massive numbers. That's believed to be when most of Earth's water and organic compounds arrived, possibly kickstarting life conditions. Earth didn't preserve a direct record of that event. The Moon did. Its oldest craters are direct scars from the bombardment. And the Farside, with its thicker crust and less post-volcanism disruption, may hold even more primitive layers with pre-bombardment material. Stuff from when the solar system was organizing, planets were forming, and life on Earth was impossible. Up to 2024, no samples from that side had been collected by any mission. We're talking about the inner solar system's greatest accessible geological archive, without ever opening its oldest pages. The origin that doesn't add up. All this talk of the Farside leads to a problem lunar science hasn't definitively solved. Where did the moon come from? The leading theory today is the giant impact. It posits that 4.5 billion years ago, a Mars-sized object dubbed Theia slammed into the young Earth with unimaginable violence. The ejected debris went into orbit and, over maybe 1,000 years, coalesced into the moon. It explains a lot. Why the moon lacks a proportional iron core, why it's relatively dry compared to Earth, why its orbit has the traits it does. But the theory has a stubborn hole no model fully plugs. Apollo samples showed the moon's isotopic composition, especially oxygen, titanium, and tungsten isotopes, is extraordinarily similar to Earth's. Nearly identical. That shouldn't happen if an external object hit Earth and the moon formed from mixed debris of both bodies. Theia came from elsewhere in the solar system with a different chemical signature. The moon should be a blend. It isn't. It looks like Earth. This spawned serious alternative hypotheses. One suggests the collision was so violent that Earth and Theia merged into a structure called a Synestia, basically a spinning rock vapor disk, and the moon condensed from fully homogenized material, explaining the chemical match. Another proposes Earth originally had two moons that slowly collided and merged, with the Farside as compressed residue from that fusion, elegantly explaining the geological asymmetry. There's even a version where Theia and Earth originated from the same solar system region with initially similar compositions, reducing the need to explain the isotopic similarity. None are confirmed. And the key to settling the debate is right where we've never properly gone. Farside rocks. If the asymmetry came from a second collision, differential heating, or some other process, those samples should differ from Apollo ones. China collected Farside samples in 2024 with the Chang'e 6 mission. Analysis is ongoing. The answer might be coming soon. The moon that rang like a bell. In November 1969, Apollo 12 astronauts ran what seemed like a simple experiment. As they lifted off from the lunar surface, they deliberately ditched the landing module, crashing it into the ground a few miles from the seismometer they'd installed. It was a calibration test. What happened made history. The moon started vibrating and didn't stop for 55 minutes. 55 minutes of continuous reverberation. fading slowly, like the surface was a shell responding to a gong strike. On Earth, seismic waves from an equivalent magnitude quake would dissipate in minutes, soaked up by our planet's damp, heterogeneous rocky interior. On the Moon, the energy kept propagating and kept going and kept going. Neil Armstrong later famously quipped in NASA backrooms that the Moon rang like a hollow bell. A hollow bell. The experiment was repeated. Apollo 13, aborting its landing, ditched the service module, and the Moon vibrated for over 3 hours. Apollo 14, 15, and 16 ran similar tests, each confirming the same anomalous pattern. The data built an entire field, lunar seismology, and what it suggests about the Moon's interior is still debated today. The lunar interior seems unusually dry, water in rocks dampens seismic waves, and the Moon appears to have very little. Its internal structure also seems more homogeneous than Earth's, letting waves travel long distances without scattering. There's active debate between models of a layered, partially molten interior and one that's more rigid and dry than any terrestrial rock we know. What makes this disturbing for the Farside is simple. That hemisphere's thicker crust completely changes the seismic equations. Waves from impacts or outgassing on the Farside propagate differently, through more material carrying info on an internal structure we've never directly monitored. Not a single seismograph has ever been placed on the Moon's far side. China's Chang'e 4 landed there in 2019, but without long-term seismic gear. We have seismic data from one hemisphere and basically nothing from the other. It's like doing an ultrasound on a patient from only the left side of the body. The magnetic Moon that died. Here's a mystery most people don't know, and in some ways, the most revealing of all. The Moon today has no global magnetic field. None. If you took a compass to the surface, it wouldn't point to any magnetic pole because there isn't one. But lunar rocks tell a different story. Apollo samples showed residual magnetization. The rock got magnetized as it solidified, which only happens if a magnetic field was present then. That means the Moon once had a global magnetic field, likely generated by a convecting liquid iron core, like Earth's today. And at some point, that field died. Lunar swirls are the most visible evidence of that death. They're huge bright patterns, spirals and white blotches stretching up to 70 kilometers, scattered across the lunar surface. The biggest, Reiner Gamma, is visible from Earth with an amateur telescope. For decades, no one knew what caused them. The leading explanation now: magnetic fossils, spots where the ancient field got locally imprinted in the rock when the global field died, possibly preserved by comet impacts that magnetized the surface unevenly. There, the remnant field still exists, deflecting solar wind, the charged particles that darken lunar soil over time. Where the field protects, the soil stays brighter. The result: these luminous patterns unexplained by conventional geology. Beneath the surface, the story continues with Mascons, dense mass concentrations hidden under lunar plains. When NASA's first orbiters circled the Moon in the 1960s, engineers spotted inexplicable trajectory wobbles, like something underground was tugging the probes at specific spots. Took years to figure out. They're likely asteroid remnants that punched deep into the crust during the late heavy bombardment and stayed there, packing mass into small enough volumes to create local gravity anomalies. They warp the gravity field enough to measurably alter a spacecraft's orbit. The Farside likely has its own Mascons, but that hemisphere's gravity map is still far less detailed than the near sides. What the Moon's magnetic death tells us is disturbing beyond the Moon itself. Understanding how planetary magnetic fields arise, persist, and die is directly relevant to Earth's own field, which shields all surface life from cosmic radiation and solar wind. Earth's field has shown weakening signs over recent centuries. The Moon is, in that sense, a case study of what happens when the shield fails. Something still happens there. Since the 12th century, serious, credentialed astronomers have reported strange events on the lunar surface, events that shouldn't happen on a geologically dead body. Light flashes, mist patches that appear and vanish, brightness changes in specific areas. The first detailed report dates to 1178, when monks in Canterbury, England, described a visible flame on the Moon's edge. William Herschel, the astronomer who discovered Uranus, an observer of impeccable credibility, logged multiple such events with meticulous detail in the late 1700s. NASA maintains an official database with over 2,200 cataloged occurrences through history. They have a name, Transient Lunar Phenomena, or TLP. The most solid instrumental case happened in November 1958. Soviet astronomer Nikolai Kozyrev was observing Alphonsus crater with a spectrograph, an instrument that doesn't just record visuals, but analyzes the light's chemical makeup. During the session, he detected gaseous carbon emissions venting from the surface. It wasn't subjective eyesight. It was an instrumental reading. The event lasted about an hour and has never been fully debunked. The leading explanation today for TLPs generally involves outgassing, gas escaping from the lunar interior through crustal fissures, possibly triggered by solar heating or micrometeorite impacts. The Aristarchus region, a young, geologically active crater on the near side, hosts most recorded events. What this implies is big. The moon isn't completely dead. At some residual level, internal processes still release material to the surface. And on the far side, with its thicker crust and potential internal differences, such events could happen regularly, without us ever spotting one. The samples that shouldn't exist. In December 2020, China's Chang'e 5 mission landed on the moon, grabbed about 3.8 pounds of lunar samples, and returned to Earth, the first fresh lunar material since the Soviet missions of the 1970s. Analysis published in 2021 revealed something the standard model didn't predict. The rocks showed volcanic activity as recent as about 1 billion years ago. That's extremely young on lunar geological scales. The dominant model until then said lunar volcanism had basically stopped 2 or 3 billion years ago, when the interior cooled enough to quit pumping magma to the surface. 1 billion years breaks that model cleanly. Something kept the lunar interior hot far longer than expected, and we don't know what. This adds to prior sample anomalies. Impact glass formed under extreme pressures. Minerals that only form under conditions the moon supposedly never saw. And water traces that should have boiled off in the lunar vacuum without some replenishment or preservation mechanism. Where does this water come from? Theories include solar wind depositing hydrogen that reacts with soil oxygen, comets and asteroids delivering water over billions of years, and the moon forming from already water-bearing material. No single answer covers all the data. Then, in June 2024, Chang'e 6 landed inside the South Pole-Aitken Basin on the Farside, collected samples, and returned. It was the first time Farside material made it to Earth for lab analysis. Early published analyses show basaltic compositions differing from near-side samples, fitting the idea of separate volcanic histories for the hemispheres. But full analysis will take years. What Chang'e 6-handed scientists could potentially settle debates on the moon's origin, geological asymmetry, and late volcanism. We're at the moment secrets are being unlocked, in real time right now as you watch this video. The ice from another time, the lunar poles have regions that haven't seen sunlight. Not in the last 1,000 years. Not in the last million. Never since the solar system formed. They're deep craters in polar zones where geometry ensures sunlight never reaches the bottom. The moon's rotation axis is nearly perpendicular to its orbital plane, meaning no seasons and these permanent shadow zones never shift. Inside, temperatures drop to minus 240 degrees Celsius minus 400 degrees Fahrenheit. For reference, that's colder than Pluto's surface in spots. They're among the solar system's coldest places. And inside is ice. In 2009, NASA's LaCrosse mission ran a historic experiment. It deliberately crashed a 2,300-kilogram rocket into a polar crater floor, while another module flew through the debris plume analyzing composition in real time. The result was clear water, frozen in that crater bottom likely since comets and asteroids dumped it there billions of years ago, preserved perfectly in the eternal freezer. But water's just the start. Follow-up missions detected ethane, carbon dioxide, ammonia, and other compounds too. And there's a possibility scientists are taking increasingly seriously, that in the deepest layers of these untouched craters, never heated or radiated, complex organic compounds could be preserved from before life existed on Earth. Primordial young solar system material frozen in perfect time capsule for 4 billion years. If confirmed, these spots are the greatest natural archive we know. and some lie along the Farside's edges in regions we're just starting to explore. The race and what's at stake. The race to the moon is back. But this time, the context is totally different from 1969. Back then, it was geopolitical and symbolic. Plant a flag, prove tech superiority, win an ideological showdown. Today, it's strategic and economic on a far more tangible level. In 2020, the US launched the Artemis Accords, a diplomatic framework for how signatory nations will cooperate and share space resources. Over 40 countries signed on. China and Russia didn't. That's no coincidence. It's two spheres of influence positioning for what's next. What's at stake in the lunar poles is mainly the ice. Water in space is incredibly valuable, not just for human consumption, but because it can be electrolyzed into hydrogen and oxygen, the basics of rocket fuel. A lunar base with polar ice access can make fuel on-site, slashing the cost and complexity of any mission heading from the moon to Mars or the asteroid belt. The moon isn't the destination. It's the gas station for solar system exploration. Whoever controls polar access controls the infrastructure of the next space age. There's also helium-3, a rare isotope on Earth but relatively abundant in lunar soil, deposited by solar wind over billions of years. In theory, helium-3 is ideal fuel for nuclear fusion reactors, clean, efficient, without fission's radioactive waste. The catch: commercial fusion doesn't exist yet, but several countries, including China, are pouring money into it, and the prospect of lunar helium-3 makes controlling specific lunar regions strategically vital even before the tech matures. China landed on the Farside with Chang'e 4 in 2019 and Chang'e 6 in 2024, and plans a polar research base in the next decade. The US fast-tracked Artemis, with crewed polar landings planned. India nailed a South Pole landing with Chandrayaan-3 in 2023. ESA, Japan, UAE all have active lunar programs. They're all converging on the same spots. The window to establish permanent polar presence is narrow, and closing faster than most realize. Here's what's truly disturbing when you put it all together. It's not that the moon hides isolated secret science will eventually crack. It's that the sum of those secrets points to something bigger. We've never fully understood the object that made life on Earth possible. Without the moon, Earth's axial tilt would wobble chaotically over millions of years, making our climate unrecognizable. The tidal cycles it drives shaped the first organisms' migration from oceans to land. The late heavy bombardment scarred on its craters likely brought Earth's water too. We're here, in part, because of it, and we still don't know where it came from, what's truly inside it, why its two sides are so different, or what's preserved in its permanent polar shadows. The moon drifts from Earth at 1.5 inches per year, a direct echo of the same angular momentum transfer that locked its rotation. On billion-year scales, it'll keep receding. In the distant future, if Earth still exists, the moon will be so far that total solar eclipses become impossible. It won't be big enough to fully cover the sun's disk anymore. Something we take for granted will vanish. Slowly, imperceptibly, but with the same physical inevitability that locked its spin billions of years ago. So when you look at the moon tonight, remember what you're seeing. Half of a 4.5 billion year archive. The other half is over there on the far side, in isolation no human has ever broken with their own eyes. With geology that shattered our models. With ice frozen before life existed. With samples that hit labs less than 2 years ago and are still being decoded. With answers to questions we've asked for millennia. The moon gazes back with the same impassive face through all our history. We're only just starting to gaze back.